In this video I'm going to be looking at the angles in standard position. And angles in standard position are terminal arms that are rotated about the origin, and they start with a rotation from the positive x-axis. So if I were to start at the positive x-axis and rotate the terminal arm through some sort of angle in the first quadrant here, if I were just to rotate through there, it would be some sort of, we can find the sine theta, the cosine theta, and the tangent theta of this angle by, again, dropping the perpendicular from this point here, and we would then know, this height here, we know this distance here, and of course we know that r is just 1. So we would find sine theta, cosine theta, and tangent theta through, of course, our favorite SOHCAHTOA. And then in addition to this, we have to keep in mind the cast rule. And there's another video on the development of the cast rule, where in the fourth quadrant, if the terminal arm stops in the fourth quadrant, only the cosine, the trigonometric ratio, is positive. If the terminal arm is in the first quadrant, all of the trigonometric ratios are positive. If the terminal arm stops in the second quadrant, then only sine is positive for that angle. And then if the terminal arm rotates and stops in the third quadrant, then only the tangent trigonometric ratio is positive. And where cosine is positive, that would of course mean that sine and tangent ratios are negative. When sine is positive, then that means of course that cosine and tangent would be negative. And then when tangent is positive down here, that would mean that sine and cosine are negative. Okay? So we also know from past experience that the sum of the angles, the interior angles of a triangle, are 180 degrees. And in another video I also showed that if we know that there's a perpendicular here, or 90 degree angle in a triangle, then that must mean that because the sum of all three angles is 180 and this angle is taken up 90, then that means that the sum of the other two has to be 90. Okay, so these two together add up to 90. And I could use some fancy software, and I may do that. I'll see if I have some time to do that. If I were to drag this point and drag it up here, this angle would get larger, and this angle of course gets smaller, because as you're dragging this forward, or dragging this point up, this vertical perpendicular would come horizontally to the left, thus making this angle at the top smaller. And so, but between them, they have to add up to 90. So this angle could get really, really big, up to 88 or 89 degrees, which would leave this angle to be 2 or 1 degree, respectively. If we drag this point back down to the bottom, this vertical perpendicular would come out to the right and get smaller as it goes, and this angle gets smaller, this angle getting bigger. This rotation would be, could be 5 degrees, then that would leave that as 85. This could be 10 degrees, that would leave that as 80, etc. So obviously between the two, they have to add up to 90. So what happens when we rotate past 90 degrees into the next quadrant? So if I were to take this point and rotate it and continue rotating into the second quadrant, well, now this angle theta is going to be greater than 90 degrees. But if we rotate it all the way around, we look at it as a reflection. And so we've reflected now this angle into the second quadrant. Here's our angle theta. It's going to be the same as this angle theta right here. So those two angles are actually going to be equal. When we talk about angle theta, the angle theta is always measured from, it's the rotation measured from the positive x-axis. So this, when we're talking about this is the terminal arm now, this angle is now going to be angle theta. And so we can't have two angle thetas. So this one we now call beta, which is the related acute angle. So notice that it's acute, it's less than 90 degrees, and it's related to this angle theta over here. Because the two angles of the triangle that are not the 90-degree angle, because those ones always have to add up to 90, we can't get any higher than that. So then when we rotate around, they just start over again. So they come over here and then they flip around, and then the angle here and angle here, sorry, these two angles, here and here, these two angles add up to 90 again, just like they did over here. So they just start over again. So they come over here, and now beta and this angle add up to 90 degrees. This is of course always 90 degrees here, and so these two add up to 90. So when we look at this reflection, this angle is exactly the same as this angle. Okay, so we could take the sine, cosine, and theta of this angle, and we can see then that we can take the sine, cosine, and tangent of this angle beta, and it's going to be the same ratio, or same ratios, as this acute angle over here. But this is where the tricky part comes in. Because the terminal arm is in this quadrant, in the second quadrant in this case, the actual angle theta that we're looking at is now an obtuse angle. But that obtuse angle is actually related to this beta angle. So the sine, and this is where of course the cast rule comes in. If we're in the second quadrant, sine is positive, then the sine of this obtuse angle is actually going to be equal to the sine of this beta angle. So we can now use this beta angle, this related acute angle, to calculate, because that's inside this triangle. It's another right triangle just like this one, just like the first one we had in the first quadrant. We can use that beta angle to find the trigonometric ratios for sine, cosine, and tangent. And so sine theta, or sine beta, sorry, is going to be some positive angle. And actually, as it turns out, beta, we always want beta to be positive. And so the sine and the cosine of beta, because this is an acute angle, we're assuming it's the same as this angle over here. And tangent, these are all going to be positive ratios, because if we're given the ratio itself, we take it as positive, and then what we do is we say, okay, well, if that's related to this angle theta, then we say, okay, well, sine beta is going to be the same as sine theta, and if it's in this quadrant, sine is going to be positive. Cosine beta, what's going to be equal, but related to this theta angle, but now in this case is actually going to be negative. So cosine theta is going to be negative of cosine beta. Okay, so we stick on the negative because the terminal arm's in the second quadrant where only sine is positive. And then for the tangent of that angle, tangent of theta is going to be the negative of tangent beta. The tangent, the actual values, the absolute value of these are going to be the same, but because of the cast rule, we're going to stick on the negative because the second quadrant is where only sine is positive, therefore cosine and tangent are both negative. So they're both going to have the same numerical value, but we stick on the negative to indicate that this angle theta is not in the first quadrant. Okay, here it's in the second quadrant, and we can reflect it again into this third quadrant and then into the fourth quadrant as well to find the trigonometric ratios for theta, for sine, cosine, and tangent theta when the terminal arm is in the third quadrant, again by using that beta angle. And now if we were to take this angle and reflect it in the x-axis now, instead of the y-axis as before, we reflect it in the x-axis, we see then that this angle down here is the same as this angle here. So this beta angle that was in this second quadrant is going to have the same value, the same size as the beta angle in the third quadrant. Now the actual rotation goes from the positive x-axis all the way around into the third quadrant. So this now, from here all the way around to here, is now the actual angle theta that we're looking at. Beta is always an acute angle, so just like when the angle was in the first quadrant, we can find the sine beta, the cosine beta, and the tangent of beta, and we're always just going to deal with them as they're positives. And then because the beta angle, and like I said before, the two angles here and here, the beta and this other angle, they have to add up to 90 because we've already got this perpendicular here, and they just keep resetting themselves as they cross the next axis. So as this terminal arm rotated more and past the negative part of the x-axis, then those two angles just started over again. Beta would be 1, then 2, then 3 as the terminal arm kept rotating, and this angle would get bigger, or sorry, smaller as this angle got bigger. Okay, so it started out as like 89 degrees, and then 88, and 87, 86, etc. as this angle got bigger, but they reset themselves, so we take beta as the positive acute angle, and it's related to this angle theta. Now this angle theta is a reflex angle because it's down is past 180 degrees. And so we take sine beta as positive, and then we just deal with the cast rule after that. So the sine of this angle theta, this actual angle theta we're looking for, the sine of that is going to be the same value as the sine beta, but because it's in the third quadrant where only tangent is positive, that means that sine theta is actually negative sine beta. Cosine theta is going to be negative cosine beta, and tangent theta will actually just be equal to tangent beta because it's in the third quadrant where tangent is positive. And so now we take this terminal arm and we flip it. Now we reflect it in the y-axis one more time, and we see that we have this angle over here, and this angle beta is here. It's the same angle as was over here. Again, the related acute angle, it's acute. The angles again continue to recycle themselves. They rebrand them, well, they don't rebrand, but they continue to just start over again and add up to 90 degrees. So now the angle theta, the actual angle we're interested in, is rotated from the positive x-axis still around to the terminal arm in the fourth quadrant where only cosine is positive. We take the sine of angle beta, the cosine of angle beta, and the tangent of angle beta, and we know that sine theta, the sine of this whole angle as rotated around from the positive x-axis, is going to be negative sine beta because this is the quadrant where cosine is positive. Cosine beta, or cosine theta, is equal to cosine beta. They're related acute angles, so of course they have to be the same ratio. And tangent theta is going to be the negative of tangent beta because of course they're related angles. So when I kept talking about the angles had to just keep repeating themselves, well, there's only 90 degrees from the positive x-axis up to the positive y-axis. There's only 90 degrees from the positive y-axis down to the negative x-axis. There's 90 degrees from the negative x-axis to the negative y-axis, and then of course another 90 degrees from the negative y-axis up to the positive x-axis, which means there's 90, 180, 270, 360 degrees of angle of rotation about one circle. So if these angles, so the beta angle and this other angle, if they have to keep repeating themselves from, say, 0 through 90, or from something very, very close to 0 to something very, very close to 90, as they continue to go around the circle, always adding up to 90, then those trigonometric ratios of SO, Ka, and Toa, they also have to keep repeating themselves. So that's why that if we have an angle here, we've got the y and the x and the r here. Because these angles are the same inside this triangle as they were over here, then the trigonometric ratios are going to be the same for here as over here. And if they're the same, they keep repeating themselves also in the second quadrant, also in the first quadrant, then that's why we say that this angle beta is the related acute angle, because beta is related to theta, but it's beta in addition to the cast rule that helps us determine what the actual complete ratio of sine theta, cosine theta, and tangent theta actually are. So they could be positive, they could be negative, depending on where the terminal arm lies. So we've looked at a bunch of different scenarios. Remember that from the cast rule, that all the trigonometric ratios are positive in the first quadrant, and then they all take turns being positive in each of the other three quadrants, which means that, and in addition to the fact that these angles keep repeating themselves, which means then that the ratios would keep repeating themselves, that would then indicate that there are two positions around, or the two positions in standard position, about the origin of the Cartesian plane, where the sine ratios are going to be equal. So in the first quadrant, we get a positive sine ratio. In the second quadrant, we get a positive sine ratio. And if the angles, the angle theta and angle beta, are equal, then that means that they're going to have the same ratio. So we could get two possible angles that give you that ratio. So you could say, well, let's try sine of 45 degrees and sine of 135 degrees. If you work those out in your calculator, you'll find that the two ratios are actually the same. We could do the same thing in the second and third, or third and fourth quadrants as well. Suppose I said sine of 135 degrees and the sine of 225 degrees. Well, in this case, they're going to have the same value, but this one, sine of 225 degrees, is going to be negative, because it's going to be down in this quadrant, in the third quadrant here. So here they're exactly the same. Here are the same values, but they're going to have opposite signs. And that goes the same with cosine and tangent as well. Cosine is positive in the fourth quadrant, and cosine is also positive when the terminal arm is in the first quadrant. Tangent is positive when the terminal arm is in the third quadrant, and also in the first quadrant. So there is always two positions, and I've just been talking about the positive values, but also with the negative values, it also works the same. Cosine is negative when the terminal arm is in the second quadrant and the third quadrant. So again, there will be two positions of the terminal arm for the same value of cosine, for the same value of tangent, and for the same value of sine. So that's why there's always multiple values of, or at least two values of sine and cosine and tangent, or sorry, of the angles that would give you those trigonometric ratios for any one ratio. Okay, so we always have to take into account both scenarios. Okay, so that's a little bit about the cast rule and about the related acute angle, and we'll take a look at some other specific examples in other videos.